Good morning, pre-calculus. So here we go. Continuing, we're going to finish up Chapter 4 today. 4.5, Interest and Annuities. So this is another exponential equation. And really a lot of the things that we're going to see today are things that we've seen in previous classes. And I want to emphasize using the formulas. And on the tests, be careful. Write the formulas down, substitute the numbers in, and then do the work on the calculator. So that's how you would show the work for this. All right, so let's take a look at what I'm talking about. So we know the interest formula, the compound formula. Amount as a function of time is the principal times 1 plus the rate over the number of compoundings. Now in the past you've used the letter n down here. I'm going to use the letter n for the number of compoundings per year. But just be aware that the textbook uses a letter k down there for that variable, to the power of nt. So for this formula, notice how many variables we've got. We've got the amount and the principal, two variables. The rate is the third. The number of compoundings, the fourth variable. And time is the fifth variable. So I should be able to give you any four of these, and you should be able to substitute them into the formula and then find the missing. So for example, the first example I'm going to give you principal and a rate, number of compoundings, and time, and you're going to find the amount. But we could work backwards. If we wanted to save a specific amount of money, and we know the rate and how long and the number of compoundings, how much would I have to invest? Or if I know how much I want to invest and I know how much I want to get back, what rate do I need? What type of compounding? How long is it going to take me? So there's a lot of variety in here in these problems. A lot of it's going to be done on the calculator, some of it algebraically. Let's take a look at an example problem. Suppose we invest $1,200 at 6.5% compounded monthly for 5 years. How much would that investment be worth? So again, the $1,200, that's going to be my principal, the amount that I'm investing. The 6.5% is my rate, but I have to put that in as a decimal. And then 5 years is going to be my time. The number of compoundings, compounded monthly, would be 12 times a year. So if we start with the formula, and again, the formula says the amount as a function of time is the principal times 1 plus the rate over the number of compoundings to the power of the number of compoundings times time. Substituting the numbers in, the amount that it's going to be worth after 5 years is going to be $1,200 times 1 plus my rate, 0.065, over the number of compoundings per month, monthly for a year, that would be 12, to the power of 12 times 5 years. So there's what we need to plug in our calculator. And as I said, in the homework and the test, write the formula down, substitute the numbers in. This will give you partial credit. I know you're using the right formula and you're putting the numbers in the right place. And if you get a mistake after this, it's just how you entered it on your calculator, which is just a minor mistake. So let's take a look at this. I'm going to put things in on my calculator now. So, and I can put this all in one step. We'll see later the annuity formula and some of the other formulas, big horrible formulas, and we might want to be a little bit more careful. So 1,200, open parentheses, 1 plus 0.065 divided by 12, close parentheses, to the power of. Now notice on the TIs and some of the newer calculators, it gives you the power, it goes into the exponent here. But on the old Casios, when you hit the little chevron button, it doesn't. I want to make sure this whole thing is in the exponent though. So on the older calculators, you might need to use parentheses. Parentheses 12 times 5, close parentheses. I didn't need them here because it's all in the exponent. But on the older calculators, make sure you're putting the parentheses there. And then I hit enter, and it tells me that the amount of this investment is worth after 5 years is going to be $1,659, and we're going to round to the nearest penny, so 38 cents here. And I could have asked the question, how much interest would you get? And I would just subtract this amount. I would subtract the original investment from this amount, and $459.38 interest. So this is very basic, very simple. You saw this in Algebra 2 and again in college algebra. Let's make it a little bit harder now where we have to find a different variable. So here we're going to invest $8,000, and I'm going to invest it at 9% interest, compounded quarterly. So I know how much I'm investing. This is my initial investment. That's my principal, P. I know my rate is going to be 0.09. Compounded quarterly means 4 times a year. And this time I want to know how long will it take for this investment to reach $10,000. So time is the variable. Time is what we need here. I'm going to start by writing down the formula. Amount as a function of time is the principal times 1 plus the rate over the number of compoundings to the power of the number of compoundings times time. That's the whole thing is in the exponent there. My principal is the $8,000. 1 plus my rate is 0.09. The number of compoundings quarterly means 4 to the power of 4t. I don't know the time, but how many years before the investment is going to be worth the $10,000? I need to solve this equation for t. And we could do this algebraically. We could divide both sides by 8,000. This is just going to be some number. So I would have some number to the power of 4t, and then I would have to use logarithms. Take the natural log of both sides, so I can move the 4 and the t in front, and then break it up and isolate that t. Or I can do this whole thing on the calculator. This kind of question wouldn't be on the non-calculator part of the test, because you're going to need a calculator either way. So on the calculator, what I'm going to do is I'm going to go to my y equals. I'm going to substitute, I'm going to type in my investment, $8,000 times 1 plus 0.09 divided by 4, close parentheses, to the power of, and again, make sure that if you've got the older calculator, you put this denominator in parentheses up there, 4, and then the variable button. So there's my growth, there's my investment growing, and I want to know when is it going to reach 10,000. So in Y2 I'm going to put in 10,000, and I want to graph this. And the graph that I should expect to see is my money growing over time. I should expect to see the starting of, let's say 8,000 is right here, and 10,000 is right here, and I should see my money growing over time. And here's 10,000, and there's the point of intersection, and this will tell me how many years. That's what I'm looking for, this graph right here. So of course I'm going to have to change the window. Remember, don't be afraid to play around with the windows here a little bit. So x is my time. Well, negative doesn't make sense, so I'm going to start at 0, and I'm going to go, I'm just going to leave it at 10 years for now. I think it'll be less than 10 years. We don't know, we're just guessing right now. Scaled in 1-year increments. My y is the money. $0. What's my maximum? Well, I know I want it to be about 10,000, so I'm actually going to go to 12,000, and I'm going to scale it maybe in 1,000 increments and graph this. Here's my money growing, and there's the 10,000 limit. Remember, Casio users, you might want to put a little extra space at the top here, because when you do calculations, it's going to write on the top there. TI users, it'll write in the gray screen here. I want to find that point of intersection. I went from 0 to 10 years, clearly less than 10 years. So I'm going to go to second trace, Casio users, gsolve, intersect. I'm going to go down to intersect here, press the button, press it again. One more time. There it is. So the intersection is 2.5. So 2.5, which means about 2.5 years. It'll take about 2.5 years for that $8,000 to grow to $10,000 at 9% compounded quarterly. Let's do another one where we have to find a different variable. So again, remember, there's 5 variables in here. I should be able to give you any 4, and you can solve for the missing one. In this one, suppose you have $13,000 to invest. Now the interest will be compounded monthly, and you want to know what rate is needed for the money to double in 10 years. So we've got $13,000 to invest, and the interest is going to be compounded monthly. Well, what rate do I need compounded monthly for that $13,000 to double, in other words, become $26,000 in 10 years? All right, as always, start by writing down the formula. Compound interest amount as a function of time is the principal times 1 plus the rate over the number of compoundings per year to the power of the number of compoundings per year times 10. Substitute in all the things that we know. We know the initial investment is $13,000. 1 plus, we don't know the rate. I'm going to leave an R in there for rate. Compounding monthly means that's a 12. 12 times the number of years. I want it to double in 10 years. So in 10 years, it's going to be worth $26,000. So again, we're missing a variable here, and we could solve this one algebraically, divide both sides by 13,000. This is going to be 120. I could take the 120th root of both sides and subtract 1 and multiply by 12. I could do this one without using logarithms. But we could also do this one graphically here. So I'm going to put it on the calculator and we'll talk about it graphically. So I'm going to go back to my y equals, clear out the things from the previous problem in here. My model, 13,000 times 1 plus my variable button divided by 12 to the power of 12 times 10. And again, Casio users, be careful. Make sure you put that whole thing in parentheses up there. And we're going to solve for the x, which is the rate, and I want it to double, so 26,000. I have to think about the window again. So as I go to my window, x here represents my rate. Now, 0 to 100 doesn't seem to make sense. My rate is going to be, that would be 0 to 10 here. I'm going to go from 0 to 1, scaled in 0.1 increments. 0 to 100%, scaled in 10% increments. And my money, I'm going to go from 0 to, well, 2,600 is going to be what I'm really looking for. So I'm going to go to 30,000, scaled in maybe 5,000 increments. And let's graph this. So here it is. There's my money growing. What happened to the 26,000? So let's see. Oh, there it is. So here it is. So it's in here. It's very close. I went from 0 to 100%, which is kind of silly, really. 0 to 100%. Remember, 1 as a decimal is 100%. I think it's got to be less than 20%. So if I had just gone from 0 to 0.2, which would be 20%, scaled in 0.01, maybe scaled in 1% increments, I might get a much nicer graph here. And playing around with your calculator to see what scale you're going to use and what the units are going to be, and maximums and minimums. It's just something you need to be able to do and play around with it. There we go. This is a lot nicer. So I need to find this point of intersection, and this is exactly what we were expecting here. Here's the money growing. Here's the different rates. So if I calculate the point of intersection here, second trace, calculate, intersect, first curve, second curve, hit enter, and it's telling me that x is 0.0695. So I'm going to say my answer is going to be 6.95%. I need an interest rate of 6.95% for my money to double, if it's compounded monthly, in 10 years. Now here's something to think about. I think about this for a moment. Does the amounts matter? What if I put $500 in here and I asked, well, how long would it take for that to double? Would it be the same interest rate? Do the amounts matter for doubling from $500 to $1,000 or from $13,000 to $26,000? Think about that for a moment. And of course the answer is no, it doesn't matter. And doubling. If we did this algebraically, if I divided both sides by 13,000, I'm going to have a 2 over here. Well, if I started with $500, time to get to 1,000, divide by 500, I would have a 2 over here as well. So it doesn't matter the two different amounts. The time would be the same. The rate would be the same. All right, let's take a look at the other interest rate formula. We should also know that we could have interest that's compounded continuously. Continuous compounding interest. Here, my amount as a function of time is equal to the principal times e to the RT, where e is Euler's constant. So this is continuous interesting. Continuous refers to the compounding period, compounding continuously here. So I've got my principal, I've got the rate and time, Euler's constant. How many variables are there in this equation? There's the amount as a function of time, principal, rate, and the actual time. There's 4 variables. And just like in the previous problem, I should be able to give you any 3 of those, and you should be able to find the missing number. I should be able to give you the principal and rate and time, just plug it in to find the amount. Or if I give you a principal and how much I want in a certain amount of time, what rate do I need, and so forth, any one of these. So let's take a look at a sample problem. So we're going to invest an unknown amount of money. That's going to be in the question. How much do we have to invest? Now, we want $12,000 in 7 years, where it's going to be compounded, the interest is going to be compounded continuously at a, so we've got 7 years compounding continuously, and I've got that. And how much do I need to put in there? At a rate of, and let's say 5.25%. So how much money do I need to invest? If I've got an account and I want it to be worth $12,000 in 7 years, and it's going to be compounding continuously at a rate of 5.25%. How much money do I need to invest in this account? Again, always start with the formula. Amount as a function of time is principal times e to the RT. Substituting in the principal, I don't know. I'm going to put my x in there. I could leave a p in there. It doesn't matter. E to the r, the rate is going to be 0.0525. And it's going to be for 7 years, and I want $12,000. Now this one, we could do this one algebraically. This is just going to be some number. E is a constant. e to the power of 0.0525 times 7 is some number, and then I could divide by that. I could do this one graphically, graph this in y1, graph this in y2. I think I'd like to do this one algebraically. So what I'm going to do is I've got my 12,000 rather, times x to the, and then I'm going to do this calculation right here on my calculator. So let's go into the mode, and I want e, so shift e to the power of 0.0525 times 7. It's going to be some number here. Here it is. 1.444, so on and so forth. And then I'm going to divide both sides. So I want to take the 12,000 divided by, I'm going to use my previous answer button here, second, so it'll divide it by my previous answer, which is still there, equals, and I get 8309 I'm going to round to the nearest penny, 56. So my final answer is I need to invest $8,309.56. If I invest that amount for 7 years, compounded continuously at the rate of 5.25%, I will get my $12,000 in 7 years. So again, focus on the formulas, writing the formulas down, substituting the numbers in, and then solving it. All of these would be problems that would be on the calculator, not on the non-calculator part, because we're going to have to be doing calculations with awkward numbers here. So solving it graphically, solving it algebraically, using properties of logarithms, however we want to solve it is all right. Show your work. Always write the formula down and substitute the numbers in. All right, what I'd like to do now, ladies and gentlemen, is I want to take a pause. This is the end of the first video. We're going to pause, take a look at the homework, do the first set of problems in the homework, and then we're going to watch the second part of the video, which is going to finish the section 4.5. So come on back in a few minutes. Take about 10 minutes to work on this first part of the homework, and then we'll finish the lesson.